In our previous video, we looked at ways to represent sample spaces that were finite. What we want to do in this video is deal with the possibility of infinite sample spaces. For an infinite number of possibilities in your sample space, an equation is one way that might be helpful to represent what could happen. Okay? And this is a little bit tricky, so let's use an example to sort of get an idea. It says assume the probabilities of having a boy or a girl are equal. We're going to assume that we're not having multiples here, there are no twins or triplets. This time we've got a couple, they decide to keep having children until they have a girl. So they're not going to have just 3 kids or 4 kids or 10 kids. They're going to have kids until they have a girl, and then when they have a girl, they will stop having kids. We want to find an equation that models how many total children the family may have. Theoretically, we have an infinite number of possibilities here because the family could have 10 boys. Then that 11th child, because it's 50-50 still, these are independent events, the 11th child could also be a boy. So they would try to have another child. The 12th child could also be a boy. The 13th child could also be a boy. Now, realistically, this couldn't go on forever. There are biological limits, there are time limits. However, we're going to assume that there are an infinite number of possibilities because we don't know how far to take this. So let's think about it with a few scenarios. First, let's think about, well, what's the probability they just have one child? Well, if we're just going to have one child, that means the birth order was just a girl, because when they have a girl, they'll stop. So the probability of a girl is 1/2. The probability of 2 children has a very specific birth order. It will be the probability of a boy first, and then a girl, because they would stop if that second child was a girl. And this has a probability of 1/4. The probability of a boy is 1 out of 2. The probability of a girl is 1 out of 2. These should be independent. So 1/2 times 1/2 is 1/4. We'll take it out one more step. 3 children. The birth order would have to be a boy, then a boy, and then finally a girl. And this probability would be 1/8. 1/2 for the first boy, 1/2 probability for the second boy, times 1/2 probability for that girl. Numerator would be 1, denominator would be 8. So this would keep going on. And so I'll say my probability for x, where x is the number of children that that family has, can be represented by the equation. It's just 1/2 to the x power. If you look at these 3 examples that we've done so far, it fits right in. 1/2 to the 1 is still 1/2. 1/2 to the 2, 1/2 squared, that's 1/4. For 3 children, 1/2 to the third, that's 1/2 times 1/2 times 1/2, that's 1/8. And so we could find all of these probabilities. We could go up to 10 children, 11 children. Those probabilities are going to get smaller and smaller and smaller. You could take this 1/2, raise it to the 10th power. So it's got this e to the -4 on the end, be 0.0000977 if you round. And that would model this infinite number of possibilities. Note that that data was discrete. The family could have 1 kid, 2 kids, 3 kids, 4 kids, but they can't have any in-betweens. They can't have 3.5 kids. They can't have 2.78 kids. What we want to look at next is how we're going to address continuous probability, continuous variables. Finding those probabilities is a little bit more complicated. Because it's impossible to list all of the single values, there are an infinite number of possibilities between any two values. We're going to use a probability density curve. So we're going to use a curve. Note that this is a bell-shaped or normal distribution like we saw back in chapter 3, and this is what we'll use most of the time. And in order to find a probability associated with a continuous variable, the shaded area underneath that curve is going to equal to our probability. That's how we'll model this. If I could find the area of this shaded region here, it's almost triangular, but it's got a curve to it. This area would equal to its probability. This would give me the probability that someone has a systolic blood pressure that is 125 or above. This blood pressure, based off the tool that we're using, is continuous. Let's look at one more example and apply a curve to continuous data. In this example, it says, supposedly a Star Metro bus arrives at TCC every 12 minutes. You know, the buses aren't super consistent, but that's what's supposed to happen. The distribution that models the number of minutes the student must wait is below in this graph. The amount of time you've got to wait is continuous. It might not take exactly 5 minutes or exactly 6 minutes for the bus to arrive, but it could be somewhere in between there. It's a continuous variable. Time is typically continuous. On part A, we want to know what is the probability a student will have to wait between 5 and 10 minutes. Here's 5. Here is 10. So we're looking at a student having to wait somewhere between 5 and 10 minutes. So 5 minutes, 6 minutes, 7.38 minutes, 8.992 minutes. What's the probability of that? Well, this is a continuous variable. I'm going to find the area of this shape. If I can find the area, it'll give me the probability. This is a rectangle, and the area of a rectangle is equal to its base times its height. And I can see that this bar, this rectangle, goes up to 0.08333. The base from 5 to 10 minutes, that's a wait of 5 minutes, times 0.08333. It says round to 5 places if we need to. 5 times 0.08333. That gives me 0.41665. So about a 42% chance you would have to wait between 5 and 10 minutes for the bus to arrive. Part B asks, what is the probability a student will have to wait more than 10 minutes? Well, here's 10, and my curve stops. It doesn't go up to 15 minutes because the bus is supposed to arrive every 12 minutes. The longest you should have to wait is 12 minutes. So we're looking at a 10 to 12 minute wait. We have another rectangle, the base from 10 to 12 minutes. That's a base of 2 minutes. The same height as the previous probability question. 2 times 0.08333 gives us 0.16666. We round that to 5 places. We're going to look at some more continuous probabilities in the next video.